Welcome to Maths with EJD. In this video, we're starting out with power series. So this first video is focused on understanding power series. And a power series is an infinite sum. It is an infinite sum of the form summation n equals 0 to infinity an x minus c raised to power n. Okay, let me push it down so I can have some space. So it is of the form summation from n equals 0 to infinity an x minus c raised to power n. And of course, when n is 0, right, you have a0 x minus c raised to power 0. Anything raised to power 0 is 1. So we have a naught plus a1 into x minus c raised to power 1 plus when n is 2, we have a2 x minus c raised to power 2, and so on and so forth. So that is what a power series looks like. And let's talk about the components of the power series now. So where the first component is an, where an are the coefficients, where an are the coefficients. So that's like a0, a1, a2, and so on and so forth, a3, a4, a5. Okay. Then, of course, you have x, which is the variable. We have x, which is the variable. That is like the main thing around which everything is happening. Then we have c. C is also important. We have c. We have c. C is the center of the series. C is the center of the series. Okay. Now, you should understand that the power series is a powerful tool, for approximating functions. You can use it to approximate functions, solving differential equations, and analyzing complex functions and analyzing complex functions in mathematics, physics, and engineering. Okay, so that's our introduction to power series. Let's talk about convergence. It's a very important concept in power series too. Convergence of power series. Convergence of power series. The convergence of a power series, depends on the value x. It depends on the value x. So the set of values for which the series converges, is known as the interval. It's known as the interval of convergence. convergence. Okay. Now, to determine this interval, two common methods are used. Two common methods are used. So we have the methods as the ratio test, the ratio test, and the root test, So these are very important methods that we use. Okay, so let's start out with the ratio test. Ratio test. So the ratio test is used to determine whether a power series converges by calculating the limits, L equals limit as n goes to infinity for an plus 1 all over an. That's where the ratio comes in. So you have an and the next, the coefficient and the next term after that coefficient. So that's an plus 1 all over an. So that's where the ratio comes. Now, so once you compute this L, right, you should check if L is less than 1, then the series converges. That's that. Then if L is greater than 1, if L is the limit now. If L is greater than 1, then the series diverges. Then lastly, if L is equal to 1, you can say the test is inconclusive. This test is inconclusive. And you may need to do further investigation to be sure. So let's look at some examples. Let's take some examples under ratio tests. So examples. 1, exponential function power series. So the exponential function power series, the power series for the exponential function, e raised to power x is summation from n equals 0 to infinity for x raised to power n all over n factorial. So that's the expression. So now, of course, if you write that out, right, you have summation from n equals 0 to infinity. Then you have x raised to power n over n factorial. You can rewrite that as x summation from n equals 0 to infinity. So if you remove the coefficient, that's 1 over n factorial, and then you have x raised to power n. So of course here the center would be 0 because this is like x minus 0 raised to power n. So here you can see already this is the coefficient. So that is the coefficient in that case. So we can quickly extract that. We know that an is actually 1 over n factorial. So if we have 1 over n factorial, this simply implies that an plus 1 will simply be 1 over n plus 1 factorial, simply. And so if you now want to use you can use this expression now to find the limit, okay? So here we have L now, which is the limit as n approaches infinity for the absolute value of an plus 1 all over an, and that is limit as n tends to infinity for an plus 1, like we have, is 1 over n plus 1 factorial divided by 1 over n factorial. So that means we have limit as n approaches infinity for 1 over n plus 1 factorial divided by 1 over n factorial. So this is limit as n approaches infinity for 1 over n plus 1 factorial times n factorial all over 1, so that we can now have limit as n approaches infinity for 1 over, of course, since we have n factorial up there, we can break this down as n plus 1 multiplied by n factorial, then that times n factorial all over 1. So this cancels this, and then we have limit as n approaches infinity of absolute value of 1 over n plus 1. Okay, so for you to do something like this, usually what should happen is divide each term by n. That means you have limit as n approaches infinity for 1 over infinity, 1 over n, sorry, 1 over n all over n over n plus 1 over n. Divide each term by that and then tidy things up. So you have limit as n approaches infinity of 1 over n of the all over n is 1 plus 1 over n. So the next thing you want to do is to substitute infinity for n. So then the limit goes away once you do that substitution. So you have absolute value of 1 over infinity all over 1 plus 1 over infinity. Now, let's see. When you divide anything by 0, x divided by 0, for instance, is equal to, is undefined, is infinity. So you can cross multiply. So you have 0 times infinity equals x times, and that's x. If you divide through by infinity, what happens? So you have 0 infinity all over infinity equals x over infinity. So this cancels out. So it means whenever you divide anything by infinity, the answer is 0. Okay, so this is useful here. So you now have 1 over infinity. So it means your L is actually 1 over infinity is 0 all over 1 plus 0, another 1 over infinity. So that means L is equal to 0 over 1 and L is equal to 0. So it means that the limit here is 0. So since the limit, and then you can now make your final decision. You can make your final decision that since L is equal to 0, L is equal to 0, and that is 0 is actually less than 1. Then you can say the series converges, for all x. So the interval of convergence, is minus infinity. So whenever you get L to be 0 like that, that's minus infinity to infinity. That's the interval of convergence. So now so the application of this, right? We have an application for this. The exponential series, is fundamental in solving differential equations. It is fundamental in solving differential equations, especially those involving exponential growth, or decay, such as population growth models, or radioactive decay, So that's its application for exponential power series. Okay, so let's take another example, which is geometric series 2. series. Geometric series. So the geometric series is given by summation from n equals 0 to infinity x raised to power n. So of course here the coefficient is 1. The coefficient is 1. The center is 0. And of course you have that power. So that's how that goes. So, and that's, if you expand it, looking at the n value, so you have x raised to power 0, which is 1. So you have 1 plus x squared plus x cubed and all that. So, okay, well, let me even talk about this briefly. This is like an aside. You have summation from n equals 0 to infinity, right? And this is x raised to power n. So when n is 0, right, you have x raised to power 0 plus x raised to power 1 plus x raised to power 2 plus x raised to power 3, and that goes on forever. And then you can tidy that up to be 1 plus x squared plus x cubed and all the rest. So this is a series for sure. And there is something about sum to infinity whose formula is a over 1 minus r. A is actually first term, r is common ratio. So the first term in this case is 1. That's the first term you have here. And the common ratio is x over 1, or x squared over x, which is actually x. So if you try to find the sum to infinity in this case would be 1 over 1 minus x. So this is important. So, and this actually gives you an idea about the radius of convergence and things like that. But that's just by the way, okay? So the main thing is to talk about the convergence. Okay, so now to talk about the convergence, right? You have summation from n equals 0 to infinity of x raised to power n. So here, if you are going to extract a coefficient, it will just be 1. So that won't make sense. So it's better you just take an to be just xn the way it is. You can do that. So then you find the limits. The limit is L is limit as n approaches infinity for the absolute value of an plus 1 all over an. And of course, from here, you can already know that this implies that an plus 1 is actually x raised to power n plus 1, like that. So that you have the absolute value of x raised to power n plus 1 all over x raised to power n. So that simply means you have x raised to power n times x raised to power 1 all over x raised to power n. Okay, yeah, the limit should still be there. Until you substitute, you keep writing that limit as n approaches infinity. So this cancels out. So you have limit as n approaches infinity for absolute value of x. So since there's no n here anymore, you can as well just say this is absolute value of x. So, and the only condition for the limit to exist, for it to converge rather, for it to converge is that whatever you get, whatever your L is, should be less than 1. So we can say, in that case now we can say the series converges, the series converges if the absolute value of x is less than 1. So the interval of convergence, is -1 less than x less than 1. So generally speaking, anytime you have the absolute value of a less than b, anytime you have that, so what it simply means is that the negative of b will be less than a itself, and a will be less than b. So whenever you have this is how to break it down. So that's why the absolute value of x less than 1 is actually -1 less than x less than 1. Okay, so let's talk about the application of this one in this case. So what's the application of geometric series? Okay, geometric series are used in various applications. They're used in various applications, such as such as calculating present value in finance, and analyzing signal processing in engineering, signal processing in engineering, signal processing in engineering. Okay, so let's consider series with factorials now. Series with factorials, that's number 3. Series with factorials. So for series with factorials, consider summation from n equals 1 to infinity for n raised power n, x raised power n, all over n factorial. Clearly, an is equal to n raised power n all over n factorial. That's like when you remove the x part, that's what you have. And then that means that an plus 1, okay, an plus 1 will simply be this. An plus 1 is equal to n plus 1 raised power n plus 1 all over n plus 1 factorial. Okay, so that you can now have the limit. So you have the limit, that's your L now. So you have L, which is equal to limit as n approaches infinity for an plus 1 all over an. So, I mean, this time we can go straight so we don't keep dancing around. So an plus 1, you can already see that that's n plus 1 raised by n plus 1, all over n plus 1 factorial divided by that is times n factorial all over n raised by n. Okay. So clearly this can become this next. So we have okay, sorry. You keep writing the limits. Keep writing the limit until you substitute. So keep writing. So we have limits till as n approaches infinity for, that's like n plus 1. N plus 1. Okay, well, the way the whole of that part is looking, right? It's actually okay, I'm trying to see a very nice way of taking care of that. Okay, so let me just go gradually. N plus 1 raised by n plus 1 all over n plus 1 times n factorial. This is because we have an n factorial up here, and this is n raised by n. So this cancels this already, and that means L is equal to limit as n approaches infinity for, this n plus 1, and there's one n plus 1 here. So if you take this one out of it, so it's more like you have n plus 1 raised by n plus 1 minus 1, dividing by this one. So, and all of that is divided by n raised by n. So we have L to be limit as n approaches infinity for n plus 1 raised to power n, n plus 1 raised to power n all over n raised to power n. Okay, so, and if you look at the whole of this, this is actually, so our L here, by the definition of exponential, right? Our L, looking at this limit, is actually the same thing as the value E. That's 2.718. That's the value, the number you have in exponential function. So, and since it's 2.718, right? So you can see that it is greater than 1. So if it is greater than 1, so you can now say, therefore, since L is equal to E and it's greater than 1, the series diverges. The series diverges. The series diverges for all x. It diverges for all x. So there is no interval. There's no interval of convergence. There's no interval of convergence. So that's how that goes. So where do you use this kind of expression? So understanding convergence of such series, such factorial series, such series helps in the analysis of complex functions, complex functions, and the behavior of series with rapidly growing terms, with series with rapidly growing terms. So you see, you can imagine why this expression is replaced with E. So if you look at it, before you move few steps, this number grows so fast so that it behaves like the exponential expression, right? That's why we can easily replace it with that exponential thing. So because in fact, if you break it down further, right, this is actually like n plus 1 all over n, all raised power n. So it grows so fast. It grows really, really fast. So that's why we can boldly exchange it with E, which is 2.718 up there. So for terms that grow very fast, this is really useful. Okay, so that is all about the ratio tests. That's about the ratio tests. Okay, we've come a long way. So let's move on to the next one, which is the root test now. Root test. So while the other one uses ratio, this one is focused on roots. So the root test again, the root test is particularly useful. It's particularly useful for series where the general term involves powers of n. So if you have power n, the root test is very useful whenever you're dealing with power n in the expression you're working with. So the limit to consider is L equals limit as n approaches infinity for the n truth of the absolute value of the coefficient an. Okay. Again, the same conditions. If L is less than 1, the series converges. Then if L is greater than 1, the series diverges. And lastly, if L is equal to 1, the test is inconclusive, just like the case of ratio test. And further investigation will be required to test for the convergence. Okay, so let's take examples. Take example 1 now. Examples now. So the first example is we are looking at a polynomial series. So for a polynomial series, this is it. Summation from n equals 1 to infinity, then x minus 1 raised to power n. So you can see that power of n. So in this case, the coefficient is actually 1. So what can we do? So we have here, an is actually 1. And we are talking about the square roots of, we are talking about the nth root rather of the coefficient. So in that case, our limit will just be limit as n approaches infinity for the nth root of 1, which is simply 1. 1 raised by any number is always 1. So, and this whatever root of 1 is always 1. So we can say, in this case, the root test is inconclusive. The root test is inconclusive. But since this is a geometric series, so you can see this is the further investigation now. So you can see that it's geometric because of the power, except that it's a geometric series, but it has a center, unlike the other one that it don't have a center. So since it is a geometric series, it converges for absolute value of x minus 1 less than 1. Okay. Or 0 less than x less than 2. So I mean, this is the idea. Okay, this is just by the way, you have if you have absolute value of x minus 1 less than 1, I've already told you this is minus 1 less than x minus 1 less than 1. So if you want to get rid of this minus 1, so you add 1 to all the sides. So you have minus 1 plus 1 less than x plus 1 less than 1 plus 1. So that is minus 1 plus 1, that's 0, less than okay, minus 1 plus 1. So this cancels out. So you have x less than 1 plus 1, 2. So that's why this is also part of this expression. Okay. So that goes. So although using the root test now, the test is inconclusive, but we know that geometric series actually have a particular kind of behavior, just like the sum to infinity thing I did previously. Okay. So we know that that can work. All right. So let's look at what's the application of this kind of series. So we can know that polynomial series are used, in Taylor and Maclaurin series expansions Now you're going to I'm going to make videos on Taylor and Maclaurin series in after at some point, right? In this series of polynomial series, in this power series rather, because they are very powerful, such that for any kind of expression you have, you can actually expand, you can get their expansion. You can get a polynomial expression for any kind of a function like trig or anything like that. So okay, polynomial series are used in Taylor and Maclaurin series expansions, which approximate okay, which approximates functions like sine, cosine, and logarithms. I think they are generally known as transcendental functions, and logarithms with within specific intervals as one application of this. Okay, that's the first one down. Then let's talk about the second example, which is alternating series. So a very good example of that is summation from n equals 1 to infinity for minus 1 raised to power n, x all over n, all raised to power n. Okay. So if you actually want to extract, we can write this as summation from n equals 1 to infinity for minus 1 raised to power n times 1 over n raised to power n. If you extract that part, and you have x raised to power n, such that you have minus 1 all over n, everything raised to power n. okay, that's summation from n equals 1 to infinity, and then you have x raised power n. So that this is like your an is minus 1 over n, all raised power n, like that. So you can now find the limit. So L is limit as n tends to infinity of the nth root of absolute value of an, that is. So that means L is equal to limit as n approaches infinity, nth root of absolute value of minus 1 over n, of course, raised to power n. Okay, so because it's absolute value, right? So we can actually say limit as n approaches infinity for the nth root of 1 over n raised power n, because 1 over, okay, let me go a bit slower. All raised power n, right? So we have L to be limit as n approaches infinity for the nth root of 1 over n raised power n. So, and you see that actually moves pretty fast also. So what happens is we have L is limit as n approaches infinity, and this is more like 1 over n raised power n, raised power 1 over n, because n root is power 1 over n, so that L is equal to limit as n approaches infinity for 1 over n raised power n, this n power here times 1 over n. So this cancels out, and we have L to be limit as n approaches infinity for 1 over n. So, and that is simply 1 over infinity, and 1 over infinity is 0. So you can say that the limit is actually 0, and it's less than 1. So we can say that since L is equal to 0 and it is less than 1, so we can say that the series converges. The series converges for all x. The series converges for all x. And the radius of convergence will definitely be the whole minus infinity to infinity, as we had before. So what's the use of this particular one? So alternating series. Why is it even called alternating series? You can see for alternating series, you have minus 1 raised power n. So when n is 0, you have positive 1. When n is 1, it's negative 1. When n is 2, it's positive. When n is 3, it's negative. That's why it's called alternating series. Okay? That's why it's called alternating series. Alternating series, and it's mostly applicable in the case of sine and cosine and all that. So alternating series like this are used, in approximating functions, in approximating functions where precision is required, in oscillating systems. So systems that keep changing, in oscillating systems, such as alternating current circuits. Okay, so that goes. Then, of course, let's take the third example for roots. So here we have exponential like series, exponential like series. So, and a very good example of that is summation from n equals 1 to infinity of x all over n, all raised power n squared again. So that's a very interesting one. N raised power 2 up there. So, of course, that's like summation from n equals 1 to infinity of x raised power n, all raised power n squared. So if you want to rewrite that, that's summation from n equals 1 to infinity of x raised power. Okay, we can bring out, so this is more like 1 over n squared raised power n squared. Oh, sorry, 1 over n raised power n squared. Then you have x raised to power n squared again. So that your an is simply 1 over n 1 over n raised to power n squared, something like this. Or better still, let's just write it the way we have it at 1 over n all raised to power n squared. Okay, so if you apply the root test, right? If you apply the root test, we have L to the limit as n approaches infinity, which is the nth root of the absolute value of an, like we know, and that is equal to limit as n approaches infinity for the nth root of 1 over n all raised to power n squared. Okay, so if that is the case, then we can say we have limit as n approaches infinity for 1 over n raised to power n squared all raised to power 1 over n again. So that's like we have limit as n approaches infinity for, so we have a kind of complicated case up there. So we have 1 over n raised to power n squared over n. That's like all raised to power n. Okay, that's like all raised to power n, because this will cancel one of this. So, and if that happens, of course I didn't bother about the absolute value again, because you know, the way it is, everything is guaranteed to be positive. Okay, so we have 1 over n raised to power n like that. And as n approaches infinity, right? As n approaches infinity, so you can already see that this 1 over n inside here will move very fast. And then because of that, 1 over infinity will be 0. And whatever else happens, this goes to 0. So L is 0. So we now say, since L is equal to 0, is less than 1, the series converges. The series converges for all x. So the application, okay, I thought I changed this. The application is that such series appear in the study of special functions, and in mathematical physics, where they describe complex phenomena like heat conduction or wave propagation. So you can see that power series are really important. So we've seen them useful in function approximation, solving differential equations, signal processing, and of course, physics and engineering. So with this, we come to the end of this video. Watch out for the next one, which is about radius, how to find the radius of convergence for series. So if you have not subscribed to this channel, please feel free to do that. And of course, hit the notification bell so you can always get alerted when a new video is released. And of course, comment, like, and share. Let me know what you're thinking. Let me know, how well you're getting this. Thanks for always stopping by. See you next time. Bye.